All right, thanks to all of you for coming. I'm very honored and excited to be here. First off, I do have some acknowledgments and thank yous I need to give. First of all this happened a long time ago because of Shun-san at ISAS, who I worked with on the CESAR project when we were proposing for New Frontiers 4. He sent me a model. I saw some things in there that I thought could be done a little better, so I provided him my building thermal models and tried to help him with some things that I thought could be improved. He provided it to other people, which I'm thrilled about. And then Shinichi-san certainly needs to get his thank you. He came up to me at the ISIS conference and recognized my name from this package, and so we started talking, and one thing led to another, and here I am today to give you the second version of building thermal models, which is really expanded on what was there as a combination of probably 3 or 4 different packages that I'd put together over the years with new material as well. So one of the things I do want to say, if you're ever without this package, as long as you have the internet, there's the NASA Technical Report Server, ntrs.nasa.gov, and this document is freely available there. So if you don't have it, as long as you have an internet connection, you could go and get it there. The other thing I do need to say is that as a government employee, I can't be recommending any commercial products, so nothing in this should be construed as an endorsement of Thermal Desktop or any other product or anything else you see in this. But since that's the tool that we primarily use, I'll be focusing today on that, but again, not an endorsement in any way. So, this package will describe the modeling that we do at Goddard. It focuses primarily on Thermal Desktop, which handles the radiative side and helps build the thermal model, and then Cindafluent is the actual solver. So all of our thermal models, as I'm sure you're aware, are really 2 parts. There's the geometric math model and the thermal math model, and 2 real solvers for dealing with that. I will discuss some of the other tools that are out there, just so you can see that it's not just Thermal Desktop. I'm sure you've encountered some of them, particularly if you've worked with the European Space Agency. They use Isatan and Thermica. If you've worked with some of the other companies in the US, you might see TMG or TSS. But again, what I'm showing you today is really meant to be informational and not in any way a recommendation of one tool or another. So this is the agenda we'll cover today. I've crossed out the things that are going to be skipped in the interest of time. When I gave this talk at Goddard, it was 2 full days of 8 hours. So you can see that we crossed out about half of it. That gives us about 8 hours today, and hopefully will be sufficient time to cover all this. So let's go ahead and launch right into it. So thermal tool overview. There are a variety of tools available to perform space-based thermal analysis. But they all do things very similarly. They compute radiation exchange between surfaces. They compute the loading from celestial sources such as the sun or albedo or Earth loading or lunar loading onto surfaces. Those feed into a thermal model along with any conductive couplings you may have, additional radiative couplings you may have to represent multilayer insulation or other internal radiation, any applied heat loads, where you've got heaters, where you've got dissipations of things using waste heat, thermal capacitance, nothing is massless. And then the logic to control what the simulation is going to do. And all of that goes together and forms an electrical analogy network model, which is then solved for temperatures. By and large, there are 2 predominant ways that things get calculated. The radiation is usually handled by a Monte Carlo ray trace. We'll go through the details of that and how it's actually getting from surfaces and properties to radiation couplings. And then the thermal computations are solving a matrix of equations or system of equations, usually in matrix form. Older versions of CINDA, it was an iterative approach to solve it. Newer versions of CINDA use a matrix inversion, which is considerably faster and definitely better. Basically, it's taking a G matrix, n by n, multiplied by a T vector is equal to a Q vector. You invert the G multiplied by the known Qs to get the temperatures. So, as I mentioned, there are a variety of tools out there. There's the Isatan TMS, Thermal Modeling Suite. Radiation is handled by ISARAD. Thermal is handled by Isatan. There's Space Systems Thermal, NX, TMG, Thermal Model Generator. This is Maya Heat Transfer Technologies, part of the Siemens product family of products. It does radiation and thermal as well. Sistema is an Airbus product, used very often on ESA projects with Airbus support. Thermal Desktop, of course, you're all familiar with. RadCAD being the radiation solver, Cindafluent being the thermal solver. And then precursor to Thermal Desktop was called Thermal Synthesizer System, TSS. and it had different modules for things. It had its own version of Fluent and a RADK and a heat rate application for doing the radiation calculations. So I did give a kind of compare and contrast what each of the tools does, looking at, what are the similarities and common things between them. What's the environment? Is it a standalone or does it plug into something else? How do they solve radiation? Do they support Boolean operations, which is one of the big strengths of Thermica and Esotan, that they can cut one surface with another and handle the radiation there? How do they handle conduction generation? What do they do for different types of objects besides surfaces, heaters, contact interfaces, heat loads, things like that? What are the model formats? Is it binary or is it ASCII? ASCII is much easier to interface with if you understand it. Binary is not. Whether you can add customized code to it, how you handle simulations. So can you just build a model and then you have to figure out all the simulation things, the different orbits, the different properties and materials and things like that offline, or can that all be done in the same package? And then what's the thermal model format? Many years ago, there was a program called Cinda-G, which did not include submodels, so you had to be very careful about your node numbering. There are codes that do include submodels that help you say, okay, well, I've got this instrument and I've got this other instrument, so now I don't have to worry if they both have a node 1000, because there's another unique identifier that keeps those separate. So I'm just going to sort of flash these up real quick and just give some screenshots. So this is Esotan. Here's a picture of a telescope for it. Space Systems Thermal. This is the James Webb Space Telescope. So I'm sure you are all quite familiar with this. We have one or two people at Goddard who have expertise in this, but one of the things that was interesting with Webb is that there were two models maintained throughout the program. One was done in TSS and Cinda-G by Northrop Grumman, and the other was done by NASA Goddard, Sean Thompson. And so they would, from time to time, synchronize those models, make sure they're still providing the same predictions, and if something appeared in one, not in the other, they would reconcile it. So that was one of their risk reduction efforts to help with the fact that they couldn't test the entire thing under flight-like conditions, just given its size. So TMG is another code that we do have at Goddard, but not as much expertise as other areas. Sistema, this is courtesy of Gerdian at Airbus. He provided me some of this information. So this is the tool with which I have the least familiarity, but occasionally I have to deal with it, so we do what we can to get it. Thermal desktop, same telescope model that you see here. And then thermal synthesizer system, again, that same telescope model. You can see that this one has the different surface types over here, and then there are different modules. So there's a geometry building module, a radiation solution module, a heat rate solution module, an orbit definition module. So rather than being all contained in one application, there are different modules within an overall encompassing environment. So as you see, there's a lot of overlap between the tools. If you were to go through all the comparisons, they all do very much the same thing. So I can't say that one tool is the best, one tool is better. I have my preferences, but that's based on familiarity more than the capabilities of this tool are far superior to the capabilities of that tool. And they are continuously improving. One tool introduces a new feature and other tools will follow along. So, but in the interest of not having to try to demonstrate how to do thermal analysis with 5 or 6 different tools, we'll just focus on Thermal Desktop today. It's the one that I know the best. There will be numerous screenshots in here from Thermal Desktop. The similar capabilities could be developed and extracted from other tools, but I will leave that as an exercise to the students. If you decide you need to do something similar to what's demonstrated here and you have Esotan, you can find the screenshots there, and maybe one of these days I'll approach some of the other software vendors and say, hey, any chance that you could do a similar presentation using the starting point, and then we could see how do I do this in Esotan or Thermica as opposed to Thermal Desktop. I did Thermal Desktop because that's where we're comfortable. All right, so at this point I'm going to sit down, and I was asked to do a quick CubeSat-like demonstration, and then we will jump into the building a Thermal Desktop model. So let me go ahead and launch Thermal Desktop here. So I'm going to do a new file. All right, so to start off, I'm going to make sure that I have the right units. So CubeSat's 10 by 10 by 10 centimeters, so let's go with centimeters. That makes things easier. And I'm sorry, I'm going to have to put on my reading glasses because my eyes aren't as good as they used to be. All right, so I'm going to turn the grid off. And I'm going to first create a thermal desktop rectangle just to get something on the screen. So here, hit the F8 key, allows me to go orthogonal. So this turns ortho on, so I'm going to go this direction, this direction. Don't really care too much about the size right now. This is going to be the base of a 3U CubeSat. And I'm going to go ahead and plan to nodalize it 4x4 with edge nodes. And then I'll come over to the surface, and I can put in the dimensions that I want here, rather than having to worry about clicking the points most accurately. So here now is a 10 by 10 rectangle. Sorry, a 10 centimeter by 10 centimeter nodalized 4x4. The next thing I'll do is I need to create the height for it. So let's go here, define the x-axis, define the y-axis. And again, now I can put in here, it's 3U tall, and I want a few more nodes upside. So we'll do it 4 by 10 tall. All right, so now I can copy this surface from here to here, and then I can use the grips to rotate that surface. So I'm going to turn off the nodes so we don't have to worry about them. And when you click on a surface in Thermal Desktop, you'll notice that you get these little blue grips here. So you can use these to manipulate the model. In this case, I'm going to aim the x-axis, rotating about the y-axis. I could aim the x-axis rotating about z, aim the y-axis rotating about z, rotate the y-axis about x. And then here you can move it to the origin. So if I just click this and point over here, now I've rotated it. So I can copy that again. Whoops, not the midpoint. This point to this point. Rotate around again. And come on, select the grip. And you can see I rotate it and line it up here. So for the last one, I'll do it a little differently, just so you can see that you can also size the surface differently. So I'll go from here to here to here, and clearly that's the wrong size. I know it's still going to be edge nodes. I know I'm going to have 4 by 10. My sizes are wrong. So I can take and stretch this distance by clicking on the endpoint and stretching it to here, and click on this endpoint and stretch it up to here. Okay. Lastly, let's go ahead and close out the box. So we'll go from here, 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 make it 4 by 4. Edge nodes. Now I prefer to use edge nodes because what happens is, if I were to do this as centroids, and I'll just show you what that looks like, I get the nodes at the centers, but then I have to figure out, well, how do I get conduction between this node to the edge and then around to the other one? So edge nodes are a convenient way to move the point locations to the edges of the surface, and then when you merge the nodes, then they'll share an edge in common. So I'll get conduction from this panel to this panel via the fact that there'll be conduction between this node and this node due to this surface, and then conduction from this node to this node due to this surface, but this node is the same because I've merged them. They're the same node number, same calculation point. So that's the easy way to establish conduction in this, and so let's go ahead and say let's merge all these nodes now. So I selected all of them, merge it, give it a minimum tolerance, and it'll tell you how many nodes it found, all the locations, and you can see right along all the edges, it zipped it up, and so now I've got those nodes merged, and so I would get conduction from one panel to the other via that. Now, certainly need to add in properties. So let me go ahead and create a database here, and we'll call this demo CubeSat.rco for Radcat Optics. We also need a thermophysical properties file. And we'll call that demo CubeSat.tdp. So I've just created a database. I don't have anything in it yet, so I need to edit the property data. In this case, rather than add them manually, I'll go ahead and import them from another file that I have. So we'll go here to Thermal Workshop, Sample Files, and I'll pull it out of the Sample Model Final. And I'm going to take the black anodized, white paint, and solar array, and No.1 out of here, import it. I'll do a similar thing for the thermophysical properties. I can access them over here, much the same way as I could through the menu. So here I'll import. Again, I'll look through sample model final, and I'm just going to pull in the spacecraft aluminum. So now I want to assign those properties where I need it here. And one of the things you'll want to check is, well, where do I have top side and bottom side? So if you visualize under display preferences for the top side, anything in green means the side that you're visualizing is the top. Anything in blue is the side that you're not visualizing is the top. So you can see that this one's got the top side facing up rather than down. So generally it's a good practice. Have all of your outs facing out and all of your ins facing in. So in this case, we're just going to go ahead and mirror the bottom surface. And so we're going to mirror it about the XY plane. And then we're going to select the point on it, which will be down here at the base, and tell it that, yes, I do want to delete the objects. And now I've mirrored it, and so the top is now facing down. Now, this may have unmerged the nodes. I'm not sure if it did or not. So just to be on the safe side, we'll go through and merge the nodes again. And no coincident nodes were found. So that looks good. Now, I do want to make sure that I have some solar arrays for this little CubeSat. So let's go ahead and copy a couple of the panels out here. Copy this here to here. And I'll just do another one over here just to move it out of the way. And now I'm going to move this from one point to another, from this point to this point. All right, so it's still going to be the default definitions for the node names. So I'm going to go ahead and make these be different. We're going to call these a solar array. So I'm going to edit these two surfaces. And I'm going to say that the numbering is going to be arrays. We'll go ahead and assign some radiation to it now. We know that this side facing out is going to be the top side. So on the top side, I'll put solar array. On the bottom side, I'll go ahead and put white paint. While I'm at it, I'll go here and assign for the conduction capacitance page that I want this to be in the arrays submodel. And I want to give it a property of aluminum. For the thickness, I'm going to double click here. This lets you enter expressions. So I could put a value in here of, 0.11, or I could enter in here. And if you enter it in here, this can be symbols, which are variables. You can also have different units. So I could say here that this is going to be, 1 millimeter instead. And you can see that it's done the conversion to centimeters from 1 millimeter to 0.1 centimeters. So I've done that, and now if I look at my model browser, you can see I've got an arrays, and then I've still got main, which is all the rest of the things that were defaulted. So I know that I can edit all of these. It's going to be the 6 thin-shelled elements, top, bottom, 4 sides. I can edit that. I also want this to be a different submodel, so we're going to call this chassis. Come to radiation, and I'm going to say, you know what? I don't think that internal radiation is going to be very important to this, so let's just go ahead and say that the top side is going to be the only side that I have to worry about radiating. And I'm going to assign to the top side white paint. And a good practice that I like to do is to the bottom side, if it's not radiating, assign a no.rad property. That way I know that I assigned this deliberately. It wasn't something that was default, and I forgot to assign it. So one of the good model checks you can do is if you have anything referencing default, and you'd like to use a no.rad, then you forgot something that needs to be assigned properly. Similarly for material properties, you want to avoid default because you shouldn't be using default properties. So no.rad, in this case, is just an alpha equal to an E equal to 1. On the concat page, I also want to put this into a submodel that makes sense, so we'll put in chassis here. Again, it's going to be aluminum, and I'll say, you know what, this is going to be 1.5 millimeters thick instead of 1 millimeter thick. And so now I get my 0.15. You'll notice this is bold. If it's bold, that means that there's a expression there. If it's not bold, then it's a plain value. If you put a comment in here, so 1.5 millimeters thick, then it should give you a light blue background behind it, which you see here. So you can tell a little bit about whether there's a comment and whether it's an expression based on the format that you see for the field here. All right, so we've done that. Let's see, what else do we need to do? I need to put some loads in this. So let's just show the chassis. And I'm going to add some symbols so that I can represent heat loads. So I either come under Thermal Symbol Manager or click the Symbol Manager over here. And I'm going to create a dissipation 1. Add it. We're going to say that's 5 watts. Do a dissipation 2. Add it. We'll call it 3 watts. And dissipation 3. Add it, and we'll call it 2 watts. Okay. Good practice, if you can, put a comment there. That way when you're looking through this field, you know what that is. So instead of just dissipation 1, maybe it's battery, and the other is reaction wheel, and the other is avionics card. The more you can document and put comments in, the better it'll be when you come back and look at something 3 months and wonder, what the heck is this? So if you document as you go, it can be very helpful. In the interest of time, I'm not going to do that though. So let's go ahead and just add some heat loads to this so we can get some dissipations in there. So I'm going to add a heat load to nodes, which will be this symbol here. So I'll select these group of nodes right here. We're going to say that that's heat's going into the chassis at that lower position, so we'll call this dissipation 1. I also want this to go into the chassis group. I like to avoid main, mainly because main, much like default, is something that if you have it, then maybe you forgot to assign something. It's always good to avoid the defaults. And I'll double click in here and I'll say this is dissipation 1. Now, one of the things, whenever possible, I always advise output to expression to CINDA. This gives you the most flexibility that it would not just be the value of this, but the expression for it, such that if you decided to change it during the run, you could, rather than having to do it from within Thermal Desktop. So whenever possible, I would check this box. That way you get the most flexibility and capability out of your model. We'll go ahead and add another heat load. Let's say it's coming in here in the middle. We got another card that's coming in there. It'll be dissipation 2. And put it in chassis. Again, dissipation 2, output to expression. And then we'll add a third dissipation up here at the top. Another card. And this one, just so we can look at it later, I'm going to leave as dissipation 3. And what you'll find is that in the output files, the CC file, you'll see that it will be values. The dissipation 3 is assigned to the nodes rather than the symbol or register, as CINDA will call it, for dissipations 1 and 2. So we'll look at that a little later, but spoiler alert. All right, so I'm getting close to having something here. One of the things you'll notice is that chassis and arrays aren't coupled by anything. So I am going to want to put some kind of a coupling between these, because this is in one submodel, this is in a different submodel. Nodes aren't merged here, so there would be no conductive coupling across there. So we're going to add a contactor. So we select the contactor, we select these 2 outer wings for the arrays, and we're going to contact them to the center chassis panel. And so here we'll say this is arrays to chassis. Again, always good to put a comment here, particularly for heat loads, heaters, and contactors and conductors as to what it is, because that way when you look in the model browser and see a bunch of contactors, you'll know what it is without having to expand further. We'll put in the chassis. I'm going to say this is an edge contactor. And so what the contactors do is they're basically looking for overlapping lengths or overlapping areas, and then multiplying it by the factor that you provide. So in this case, we're just going to say, in the interest of giggles, it's 0.1 watts per centimeter Kelvin. I like to set the tolerance to something that makes sense. I don't like a huge tolerance because that may contact some things that aren't supposed to be. So if I expect them to be close, I want them to show that they're close. And so I put in a small tolerance. I usually get rid of the apply the thickness. And you'll notice that down here I've got a size along all 4 there. So I'm not sure which sides those are, but you can see here that these are the contact locations. It shows you the little green arrows here for the sides that are going to make contact, and then this orange arrow in the middle is a to surface that the contact would be made to. So I know I'm not making contact at this edge. I know I'm not making contact at this edge. So let me go ahead and edit this and try to figure out which ones are the best ones for it. So let's just guess and uncheck the first one and see what happens. And lo and behold, now I know this is the wrong side. So I'm going to have to edit this again, not the surface, but the contactor. And I know that instead of being along y at x0, it needs to be along y at x max. And so I can infer from the other side that it needs to be along y at x0. And so now I should have both of my arrows lined up with where I want them to be. I can then, and I always recommend, make sure that it's making contact. And so you've got this show calcs down here when you've got the contactor selected. Alternatively, you could use this button over here, which is basically show contactor markers, and then select contactor, and then turn off the visibility of the surfaces and the nodes, and you'll see where it made contact with these yellow lines. If it's red, then that means that it didn't make contact. And so you always want to check your contactors, that contact is made as you expect it to be. Also be careful with contactors. If you have things that move as a function of being attached to an assembly, you might make contact at one point, but then it moves and now it doesn't make contact again. So you do have to be careful with that. All right, so at this point we've got a lot of the model built. We do need to figure out that we're going to put this into some kind of an orbit. So we'll go to the orbit manager and we're going to add a beta 25 orbit. And so we'll specify that it's at 595 kilometers, just pick a number. It's going to be a 25 beta angle. And in this case, I'm going to say that the orientation is plus z towards nadir, and plus x will be along the velocity vector. So my plus z is in nadir. I want this face to be facing the Earth, and then to be flying along that way. So I need to rotate this whole thing. So generally speaking, it's a good idea to turn nodes on for this, because if you have built your model using finite elements and you rotate them, you have to rotate and move the elements. If it's surfaces, then you can rotate or move the surfaces. But elements are defined by their nodes. Therefore, if you wish to reorient or redefine an element, you have to use the nodes to do that rather than the element itself. So we're going to rotate 3D. I'm going to select everything here. And I'm going to want the z-axis to be here. So we'll rotate about x. We'll rotate about x by 90. So I'll pick 0, 0, 0, rotate by 90, and did I get that right? And then you can see it's gone funky with the contactor, so we'll reset that. All right, so I got my plus z in the right direction, but my x-axis is wrong. I'm not flying in that direction, I'm flying along the long axis. So we'll again do a rotate 3D, select all the objects, and now I want to rotate about z, 0, 0, 0, and we'll rotate by 90. All right, so now I fly in this direction along x, plus z is pointed towards the Earth. So if I visualize this in the orbit, I can come here and say, let's show the vehicle. And so here I've got my beta 25. View this here and see that, okay, yeah, array's there, but I'm actually going to want to tip this 25 degrees in order to get the arrays orthogonal to the sun. You just double click it to edit it. You could also click the edit button and select the orbit. That will allow you to bring up the orbit manager here. And so I'm going to rotate about the x-axis by minus 25 degrees. And that's going to now put this edge onto the sun when I'm at the subsolar point. So I can then go and see, okay, does this do what it's supposed to as I go through the orbit? So I can cycle through the different points and see that it's doing what it's supposed to. That looks good so far. We'll do another check, make sure that I have assigned optical properties. All right, good, nothing default. I can list by thermophysical properties. No defaults there either, so that looks good. So let's go ahead and just run this and see what happens. So we're going to now create a case set, change the name of the group, and we'll call it Demo CubeSat. I like to, in general, Keep my Cinda files the same name as my case sets if possible. And so I'm going to now define what the simulation is going to do. So we're going to calculate radiation. We're going to generate the conduction and capacitance. We're going to build the model. We're going to run the model. We're going to post-process it. So I need to define the radiation tasks. So here I'm going to need my RAD-Ks. So I can say, control, let's go ahead and do a few more than 5,000 rays. I'm going to use 1% error, and I tend to like to use No.1 for a cutoff. RAD-K output. It's always an indicator to me of somebody who hasn't been doing this long when I see the default names here. Just take a few minutes and name this to something that makes sense. Demo CubeSat.k. Because what you'll find is otherwise you've got 5 different cases that you ran, and you got a CA10.k and a CA30.k, and you have no idea what any of them mean. So if you just take a little bit of time and name your file, it will save you and give you some intuition when you look at your file names to know, oh, this is a beta 0 beginning of life case and a beta 50 hot end of life case. Also, I like to give a submodel name that makes sense. So we'll call this CubeSat RDK for RAD-K. We're going to output until we get 95% of the sum of view factors. Cut off here. And then we'll also need, whoops, I don't want 215,000 rays. I just want 25,000 rays. Okay, so that's the radiation couplings. We also need an orbit. So let's go ahead and add a heating rate. And we're going to use the beta 25 because that's the only one we've defined. Again, I'll pick 25,000 rays, 1% error, and No.1 for the cutoff. Heat rate output again, name it something that makes sense. Cube .hr. Here I'm going to, again, give it a name that makes sense, CubeSat heat rates. All right. Okay. So at this point, it should be ready to run. Let's see what happens. Okay, duplicate IDs. Told me something that I got to go check and see why this is. Probably it's the solar arrays. So I didn't want duplicate IDs. That means that I got 2 nodes that are the same node number but not at the same point. So let's cancel running this job. And I can check and see where they are. Oh, lo and behold, they're all the arrays and some chassis nodes. So let's go see what happened there. Come back here. So let's do, I'm going to edit this array panel. And I'm going to start the numbering at 1,000. I'm going to edit this one and do it at also 2,000 so that I know that it's different. So I merged all the nodes, but there were duplicate nodes because I had copied these. So those may have been merged, but not renumbered. So that was an error on my part. I forgot to do that. So if I bring up just the chassis, I can then renumber the nodes, which is this renumber button here. Select these and say they're all 1001. If you've read through my building thermal models, you'll probably remember that I suggest always number something so that when you see a node 1, you know you probably didn't do it if you always start with 1,000. So let me be more thorough and check. Okay, the arrays start with 1,000. Chassis starts with 1,000. Okay, I numbered these. If I had looked earlier and saw 1s, I would have remembered that, okay, I didn't number them as I should have. All right, so now we'll try and run it again. Okay, so here we go. We've calculated the RAD-Ks. We're calculating the solar albedo and planet for all the positions. Going to compile, link, run thermal desktop. And here are my temperatures. I don't really like it in Kelvin. Not for a CubeSat. Let's change it to C. And it will do the adjustments here for you. So I get temperatures at minus 14 or so. Pretty chilly. So let's plot and see what happened to those. Pick one of these temperatures and plot it, see what happens. Lo and behold, I got nothing. Well, why is that? Well, the default for a case set is that you just run steady state. And so I had no data to show for transient. So let's go back and say, let's go and add transient capability to this particular model. So under under calculations, I'm going to check the box for transient. And then I'll double click here in the end time and say I want to run it 3 times HR period, which HR period is a symbol that's automatically created Based on the orbit that you have selected, it'll tell you what the period is. So this will be 3 orbits that will be run. So now I can go ahead and run it again. Doesn't take too long. Doesn't need to calculate the rad Ks. It just needs to rerun the Cinda. It has quite a bit of smarts built in to figure out what it needs to recalculate and what it doesn't. And so now if I were to plot this, I can see what's going on. So a little chilly. I might say, you know what, this is colder than I want to be. Let me go ahead and add a heater to it. So that's the basics for the demo, just for the CubeSat. Are there any questions now before I launch into building a TD model? So are you interested in the number of rays you should fire or the number of rad Ks of output that you should include? Ray number. Usually, early in a program, run it with 30, 35,000, run it with 300,000, see what the temperature differences are, and if they don't matter, you know you can run with 35,000. We did some studies a while ago on the Roman Space Telescope where we fired a whole lot more rays, but we ended up outputting about the same number of rad Ks, whether I fired 30,000 rays or 3 million rays, because I fired 3 million rays and I get a whole bunch of tiny little rad Ks because there weren't many rays that contributed to them, and we filter them out. So I could spend it and fire 3 million rad Ks and then throw 95% of them away, but that doesn't really make sense. But early on, as you're flushing out your design and you're running your models, it's good to do a sensitivity check and really say, okay, I ran this with 3 million rays, the temperature differences were 1/10 of a Kelvin. It doesn't matter, you know. But okay, with 3 million rays on this cryo region, okay, it was a 5K difference. That area I might want to pay a little more attention to. So it is very problem specific. I usually start with about 30, 35,000. That seems a reasonable number to me based on my experience. 5,000 seems a little low. So I don't like their default. So that's where I would start. Does that answer your question? Okay. Any other questions before I continue? There are ways to output the comments, but it will require you using the OpenTD application programming interface. So there's not a way right now to output the comments directly. That said, you could poll surfaces in a model and get the comment field from it and send it out. Alternatively, many of the comments are written to the CC file. So if you have a comment for a heat load, there'll be a comment block right before the logic for that heat load that says, this is heat load such and such, you know, or conductor such and such, or contactor such and such. So sometimes the information might be available in the CC file, which is a text file. Other times it may not, and you would use the API if you wanted to try to extract that documentation for a report or something like that. So it can be done, but it's not clean.